All right, so let's look at section 4.5 here, talking about completing the square. It's one of our methods that we're looking at solving quadratic equations. We've already looked this chapter at graphing them and finding their intercepts, which are the same as the roots or the zeros of the function. They are the values that make the equation equal to 0. And the last section looked at imaginary numbers that occurred when you had square roots of negative numbers, so that brought those into play. Now, completing the square is a great tool to use when we don't have things that can't be factored, and when you graph them, then you don't get whole number results. So the problem with non-whole number results or non-integer results is that you're rounding, and those aren't exact results. So we're going to look at how we can get solutions to quadratic equations, even though they are not integer results. They'll still be exact, unrounded, and they'll give us a better idea of what our solutions are. So before we do that, completing the square stuff, we have to go back and talk about perfect square trinomials a little bit and what they are. So over here on the left-hand side, we have a general form of our quadratic equation, ax squared plus bx plus c equals 0. And over here I have a specific example. I'm going to use that to illustrate this a little better. But a perfect square trinomial it follows a couple rules. Number one, you have the first and last terms are perfect squares. So first and last terms are perfect squares, meaning that if I take the square root of this ax value and the square root of c, they will both give me integer or whole number results. So if I had like 5x squared, 5 is not a perfect square, so it doesn't work. So I need to make sure that I have perfect squares beginning and ending the result. If I look over here at this specific example, 9x squared, that's a perfect square, so that's okay. 4, that's a perfect square. So that kind of qualifies that first statement. Now, the relationship between the first and the last and the middle is what makes this a perfect square. So how that looks in the general form, it looks a little funky, but we'll start there and then we'll go over here and show you what I mean by that. So basically what the relationship is, if I take the square root of a times c, okay, so if I take my leading coefficient and my constant and I multiply them together, and I take the square root, and if I multiply that by 2, that will be the same thing as b. All right, so if I take a, I take c, multiply them together, get the square root, double that value, I will get b. Okay, so let's apply that to a specific problem here and kind of see how that all works out. Okay, and you can do it two different ways. You can multiply a and c first and then take the square root, or you can take the square root individually and get the result there. So we'll look at that as we go. So I know here a is 9, c is 4. 9 is a perfect square, so is 4, so that's a good start. All right, so if I look at that square root of 9 times 4, well, that's the same thing as the square root of 36, which is the same thing as 6. Now we said this is the key right here, if I double that result, so multiply it by 2, I should get the same as my middle. That's equal to 12. Well, if I look what I have, that's exactly what that is. So it's 12. That's fantastic. That means this is a perfect square trinomial. And why we even look at this is that it factors a very specific way. If I was to go and take this particular problem and factor it like we have in the past, I have a trinomial, so I make a little box. Okay, so, put my box here. I have 9x squared. I have 4. Multiply them together. I'll get factors of 36 that add to 12. That's 9 and 4. Or I'm sorry, that's 6 and 6, excuse me. 6x and 6x. Okay, if I bring out my factors, I have a 3 and an x here, and a 2, a 3 and an x here, and 2. If we notice, these are exactly the same. So this will really factor into 3x plus 2 and 3x plus 2. Well, that is the same as 3x plus 2 squared. Okay. And why that's important is if we remember our stuff we talked about yesterday, solving quadratics by using the square root. If I can take the square root of a result over here, I can simplify it even farther. So um, we have this as well. If we can get it to a perfect square, that makes it easy because then I can take the square root of both sides at that point. So this guy, if we know it's a perfect square, this goes back to um, our 2 times the square root of 9 times 4 will equal 12. Okay. If I know that's true, I can go right to this result then. And if I look at what that is, 9 and 4, well, that's 3 and 2. That gives me that result. So let's apply that now to this particular problem right here. Now notice I have 4x squared minus 20x plus 25 equals 18. It's not equal to 0 yet, but that's okay. If I brought this over and made it equal to 0, I wouldn't have um, anything that works for me. Okay, so it wouldn't be factorable. You'd find it wouldn't be factorable. So again, this is good for when it's not factorable. So let's look and let's see if this is a perfect square. And let's break it down. So, well, 4x squared, that is 2x and 2x. If that's perfect square. 25 is 5 and 5. Okay. We said if we take that, that's taking the square root first this time. If we do 2 times 2x times 5, okay, there's that a times c part. Does that equal 20x? Again, forgetting about the sign here so far. I'm not worried about that. Well, 2 times 5 is 10 times 2, so 20x is the same thing as 20x. That's true. So this left side is a perfect square trinomial, which makes it really easy to factor. If I notice how this factored up here, 9x, well, that gave me a 3x. 4, that gave me a 2 in my final result. So I can go straight over to this and say that this is a perfect square trinomial. It'll be equal to 18. And inside here, I throw a 2x, this guy. I throw a 5, and then my middle sign, again, is all what it's about. That becomes minus. So I've now gone and factored that completely. And now I have a problem. I can take the square root of both sides. I can't take the square root of both sides up here because I have all this extra junk that I have to deal with. Here I have a single term with a single term, so I can take the square root of both sides. So doing that, take the square root, take the square root. That'll break down into 2x minus 5 will equal the square root of 18. Okay, I'm going to move this stuff down here for the next piece. So I have some more space here in a second. Okay, and if I continue solving this, I'm going to add 5 to both sides. Now again, we got to be careful here. This is a square root. This is not, so I can't add those together. So 2x will equal 5 plus the square root of 18. Okay. And then again, divide by 2. And I'm going to divide them individually by 2 here so we can see what our result's going to be. Okay. Now, this is 5 over 2 plus 18. We break that down. Again, 2 and 9, 3 and 3, looking for pairs. There's a pair of 3, so I can bring that out. The 2 is what's left over. That stays underneath. And I'm over 2. So this is going to be my result right here. Now, one thing we have to realize, when I take the square root of both sides, it actually creates a plus and a minus. A plus and a minus. So this is a positive and a negative piece. So that factors into my answer in the end. I have a positive and a negative 8 squared 18. So I need a positive and negative in my result. Okay, so that's a quick review there of a perfect square trinomial. In the next video, we'll talk about how to actually use completing the square and how it relates to this. So what we'll see in the next video is if I don't start with a perfect square, how can I create one and go from there? So that's our video on perfect square trinomials, and we'll move on here in a minute.